Hello everyone, welcome to this session of Students Learning Seminar. Today's talk is by Soham Bakshi, a student of BMath second year. The topic he will talk on is on the sets of points of continuity and maximally discontinuous extensions. Please start, Soham.
Thank you very much. And okay, so firstly, should I keep my video on while the presentation or can I keep it off?
Yeah, you should keep your video on. If there are lags, I think you can turn it off in that case.
Great. Great. So to start with, so this is a very kind of long and boring name of the topic. So let's start the interesting part of it. Like, how are we arriving to it? So firstly, our problem is that we want some function from R to R, a real valued function from R, which is continuous on irrationals and discontinuous on the rationals. So this is quite a famous one. And example is the Thomas function, or it's also called the popcorn function, which is it is all 0 at the irrationals and 1 by n for m by n when m by n is a rational representation. So you can check that this function is continuous on the irrationals and discontinuous on the rationals. Yeah, so I will not check that now, but yeah, you can check that. And then there is like obvious extension of the question, not extension, a variation of the question, that can we have a function from R to R which is continuous on the rationals and discontinuous on the irrationals? We're just changing the roles. So and you can think about it for a while, and the answer is no. And so the main theme of the today's presentation is to get that answer, and then we'll also do many other things. But yeah, so our main motivation is to get a to prove that there doesn't exist any function from R to R which is continuous on the rationals and discontinuous on the irrationals. So what is the general formation of it? The thing is, we have a metric space. We can do it in a metric space, or you can just do it in a topological space too. But for now, let's stick to the metric space thing. So let A be, XD is a metric space, and let A be a subset of X. So now we are asking that can we get a function from a real valued function from X, which is continuous exactly on A and not outside A. So yeah, there is this notation I can. So for a function f, we write this thing. This is all the points x where f is continuous. We'll see this notation later, but okay, anyway, so clear it now. So what are we asking? We're asking for a given metric space and a given subset of it. Can we get a function for which the set of points of continuity is exactly that set, that subset of x? So let's see, if, like, of course, we know that there are many A's, like many subsets of X for which this is possible. And also we stated that it is not possible if A is rationals, like there can't be a function which is exactly continuous on the rationals. We haven't proved that yet, but yeah. So firstly, A is not all possible subsets. So for any subset of X, you can't do it. So then our thing is we want to characterize the sets for which we can do it. That is, we want to characterize the sets which can appear as a set of points of continuity for some function f x to r. Yeah, and the second thing what we are asking is slightly stronger than the first thing. In the first thing, we are saying that given a, we need to find a function f for which this happens. So in some sense, in the second question which we are asking, we are also including the other direction of it. That is, given a function f from x to r, can we say something about the set of points of continuity of it? So that is what we are asking now. So for that, we need some just basic definitions. Many of you might be familiar with it. So I will just go through it. What is a G delta set? Let X be a metric space. Again, we can do it for any general topological space, but for now, let's stick to a metric space. So let X be a metric space, then a subset of it is called G delta. if it can be written as a countable intersection of open sets. Okay, so first of all, it might not be open. Finite intersection of open sets must be open, but countable might not be open. So this is a like these are non-trivial sets, like not all open sets are like that. And then we define F sigma sets very similarly. We take the sets which can be written as the countable union of closed sets, and we call them to be F sigma. So let's see a few examples. Clearly, if A is G delta, then A closure, A complement is F sigma. Right, this is trivial because if you take the complement, the intersection will become the unions and the open will become closed. Then any open set in G delta, any open set is G delta and any closed set is F sigma. That is also very trivial because you can just write it as a countable, like countable means one. Any open set can be written as that set itself, which is the intersection of one open set, that is that set. So like that. Now, which is a little bit non-trivial here is that any closed set is a G delta set. So how to say this? For a closed set, what we do is we see that it can also be written as the intersection of the sets of this form, What is x in x is that dxa is strictly less than 1 by n. So what is dxa is the supremum of the distance of any point in A with x. So that is less than 1 by n. So this is the set of all points in x which is having distance less than 1 by n with x. So if we take the intersection for over n, then we will get A because this actually we get the points of A and the limit points of A. So okay. So if A is closed, then this is equal to this. And now you can also check that all these sets, this x in x such that dxa is less than 1 by n, these sets are open. Okay, and that is also not very hard to check. And so we can say that any closed set, so we are writing the closed sets in the way of countable intersection of open sets. So any closed set is G delta set. Similarly, now if we can take the complements and we can prove that similarly, we can prove that all the F sigmas are like any open set is F sigma set. Sorry. Now any countable set is also F sigma. This is also very trivial, like a countable set is a closed set. So like this, we just went through the examples to get comfortable with the definitions, nothing else. Okay. So now we will go to the main theme. So that is the points of continuity. So given a function from x to y, let there be two metric spaces x and y. So a function from x to y. So what we can say here is, we know the definition of continuity. So a function is said to be continuous at x if this happens, this thing, which is a very formal and the definition we all know from real analysis. So this happens. So there are two equivalent ways to write it. So I will just state them because we need the equivalent definition actually, not this one. So f is continuous at x if for all n in n there exists a open set containing x naught such that f of u is in the 1 by n neighborhood of fx naught. That is also, this is same as the definition we gave before. And again, which is equivalent to saying that for any, it is continuous at x naught if for any n, there exists open neighborhood around x naught such that the diameter of f of u, that open neighborhood around x naught, is less than 1 by n. You can check them that all of the above are equivalent. So yeah, so we'll work with the third definition and see how we can write the points of continuity of a function. So again, given two metric spaces, we're taking a function from x to y. So let's define that notation we saw before, that C of f is the set of all points in x at which f is continuous. Then what we can do is we can write it as the countable intersection over n for x in x such that u is an open set containing x and diameter of f of u is strictly less than 1 by n. So Why it is a set of points of continuity? Because if there is, we can just check the both way inclusion, and of course it is, if it is continuous at some point, then that point is in the intersection of, that point is in all the, like for all n, that point is in this set. So this will be in the intersection, and again the reverse also, converse also, you can check the other side of the inclusion. So this, let's name this On. On is a set of all x, x in x, capital X, such that there is an open neighborhood of x having diameter less than 1 by n. Diameter of f of u less than 1 by n. So if we define this to be On, then we'll prove that this On is open. And that is all we need to prove, because like to prove that the set of points of continuity of any function is a G delta set. So we'll prove that. So this is our first result. We will prove that if xy are metric spaces and if it's a function from x to y, then the set of points of continuity is a G delta subset of x. Now, two remarks before we go to the proof. The proof is not much left, but before that, this is not true for any, like not true, like the proof will not work for topological spaces, like if x and y are two topological spaces. But we can change x to be any topological space and y to be any metric space. In that case also it will work, and the same proof will work. Okay, so yeah, and like what I'm trying to say is that we'll need the distance function of y in our proof, because we just use them also here, because diameter is something which we define in a metric space. We need the distance for it. It's not a topological property. Anyway, so what is the proof? So how we prove it? We need to prove that On is open for all. To show that On is open, we need to prove that any point of On is an interior point. For that, we check that if x is in On, then there exists, was a definition of On. By the definition of it, there exists a open neighborhood of x such that the diameter of f of that open neighborhood is strictly less than 1 by n. So then you take any point in that open neighborhood which you got for the x. So let that point be y, and that y, for that y also you can take the same open neighborhood u, and you will get the diameter of f of u is less than 1 by n. And so y is also an element of On by definition of On. So this whole set which you took u, the open neighborhood of around x, is a subset of On. So we can conclude that On is open because any point in it is an interior point. So this is done. So what did we prove? That we proved that for any two metric spaces x and y, if we take the function f from x to y, then the set of points of continuity is a G delta subset of x. Now what we prove is what we started with. Can we have a function from R to R which is continuous on rationals and discontinuous on the irrationals? So we'll prove that this is not possible. To prove this is not possible, what we need to prove? We need to prove that rationals is the set of rationals is not a G delta subset of R. That is all we need to prove, right? So we'll prove that. So that requires this Bayer category theorem, a version of it. So what we'll prove is that rationals are not G delta. So just assume for the sake of contradiction that rationals are G delta. Then Q is written as the countable intersection of open sets, say On. And then you take the complement of Q, that is irrationals, and that can be written as countable union of On complement. On complement, they will be open sets, right? Sorry, closed sets. On are open sets, On complements, they are closed sets. Now, just take the other rationals also. So you just take union with the rationals, both the sides. For that, you will get irrationals union rationals, that is the whole R set of reals. And the other side will be the countable union for each rational number, and then the countable union of all the closed sets. So now we have to check two things, that On are open and dense. On are open is known, and why On are dense? Because On contains all the rationals, and rationals are dense. So On are dense. And thus On complement are no at dense sets and closed. Okay. So, and also Q are also no addend sets. And the singletons are always no addend in R. Then what we can do is, by this thing, we are writing R as a countable union of no addend sets, which is not possible by Baker-Category theorem. Okay. So thus we prove that Q is not a G delta set. Great. So this is something we are able to prove. Now we don't stop here. We want to do something else. So again, we are going to the second question of ours we started with. So what are we asking? We are asking that let X be a metric space given a G delta subset of it. Can we have a function f from X to R such that it is continuous exactly on A? This is something we are asking. So we got the other direction that if it is continuous on some points, then the set of points on which it is continuous is a G delta subset of the metric space. Now we are asking the opposite of it. So this is not exactly true, okay, but a very small restriction on it will make it true. So we'll see that. So firstly, why it is not true always. So the example is take some metric space with isolated points. So if that is the case, then we all know that any function from X to any metric space Y must be continuous on all the isolated points, right? Because you can take a neighborhood around it which doesn't contain any other point, and that will map to exactly that f of that point. So you can do it that way and prove that it is continuous on any isolated point of X. So now, yeah, so what is the problem here? The problem is if we take a G delta subset of X, which doesn't contain doesn't contain all the isolated points. Okay, so we can have many such G delta subsets of X, right? In that case, it can't be continuous exactly on the G delta subsets because it also must contain all the isolated points of it. So what we can say here is like this, that if suppose H is the set of all isolated points of X, then what we can say is that H is a subset of for all function or any metric space. So now if we take a G delta subset here, let's say, which doesn't completely contain this H, then we will not get any function from X to R for which CF is equal to A because it doesn't contain H. But so this is a very trivial counter example of the previous statement. So what do we do now? We restrict ourselves towards the metric spaces which are perfect metric spaces, like not containing any isolated points. So for that, we want to prove the previous thing. That is, given any G delta subset of X, if X is a perfect metric space, that is a metric space without any isolated points, then if we get a G delta subset of X, given a G delta subset of X, we'll always get a function such that C of F is equal to that G delta subset of X. Okay. And how can we extend this if we prove this? So first of all, we need to prove this, this version of this for X, a perfect metric space. So we will prove this. This is true for a perfect metric space. Now suppose, assume that we proved this. And then what we can say for in a general metric space? We can say, you can just check it. It is very easy to check. If this is true, what I said before, then for any general metric space, we can just take a G delta subset which contains H. Like we can say that for any G delta subset A containing H, we can find a function f such that f is continuous exactly on A. That is also something we can say. So, so in that way, we are not losing much by forgetting about the perfect metric space, forgetting about the metric spaces with isolated points now, for now. So that's it. So we'll now try to prove that for any perfect metric space, if we are given any G delta subset of it, then there exists a function which is continuous exactly on that G delta subset. So this is something we want to prove. Okay. Yeah. So that is what I said. X be a metric space without isolated points. Then given any G delta subset of it, we get a function such that this happens. So combining it with the other thing we proved, that is for any given function from x to y, the CF is always a G delta subset of x. X to y, y a metric space. So combining these two, what we can say is that let X be a metric space, and the set of, and again combining the comment I did before, that you can, for not perfect metric spaces, we can just extend it like that. So assuming that is also true, we can finally, what we can say is that if X is a metric space and the set of isolated points of X is H, then this sets which appear as a set of points of continuity of a function defined on X is same as the G delta subsets of X containing H. That is again for all. So like we can write it like this. Just another way to write it. Sorry. H is a subset of A, subset of X delta. This is equivalent of saying that there exists function f r. So this is what we are saying. So we are actually able to characterize the set of points of continuity for any function from a metric space to a metric space. Okay. Because here we can see that there exists a function x to r is same as saying there exists a function x to any metric space y. If we can change y to any arbitrary metric space. Of course, if we fix y to be something like singleton or something, then this is not true. So we're not going in that way. That won't be a very interesting way to go. So this is our statement, and we want to prove it. So let's see how to prove it. So to prove this, we need a pretty well-known lemma, which says that if X is a metric space without isolated points, then there is a dense subset A such that the complement of it is also dense. Okay, so for example, in R we have rationals, and the complement of it is the set of irrationals, which is also dense. Both of them are dense. So I think we can prove it. We'll have time to prove it, but let's skip the proof for now. If we get time, then we can go through the proof. The proof is very interesting and involves John's lemma and stuff. Okay, so for now, let's skip the proof. We can prove it that this is true. So given any perfect metric space, there exists a subset which is dense and whose complement is also dense. Okay, so now we are proving our result, our theorem, that for any given G delta subset of a perfect metric space, we'll find a function which is continuous exactly on that subset. So let A be a given G delta set, okay, of a perfect metric space. Then what we can say is A is written as countable intersection of open sets, of course. And then again, A complement can be written as countable union of closed sets. And if we can write it as countable union of closed sets, we can also write it as countable union of the increasing sequence of closed sets. Right, that is something very obvious. But okay, to check this, you can just write it in some way, then just take the union of them and go on, and that is a way to write it like this. Anyway, so if we get this, A complement equal to union of countably many closed sets in this increasing fashion, then yeah. So now we define a function. What is our aim? We want a function which is exactly continuous on A. So, and so it is also discontinuous on any point except which is not in A. So we want a function like that. So what we are doing here is, so X doesn't have any isolated point. So there exists a subset of X, say B, such that B and B complement both are dense in X. Okay. Then check the indicator function of B, that is, which is 1 when X is in B and 0 when X is outside B. So we define a function in this way: fx equal to gbx minus half. What is gbx minus half? This takes gbx minus half takes half when X is in B minus half X. Right? And then we multiply it with the sum over k of 1 by 2 power n. And what is k? K is the set of indices for which X is in Fn. So this depends on X. So better written as kx. This is all the n such that X is in Fn. Okay. So this is something like, suppose X is in F2, then X is in all the sets, right? So k is then n greater than equal to 2 for n. Like that. So again, something we can check here: if X is in A, then what is the value of, like, what is kx? Kx is the empty set, right? And if kx is the empty set, then if this is 0, sum over empty set is 0. So f of x is equal to 0. So for any x in A, we can say that f of x is equal to 0. Okay. And again, in the other direction, if x is in a complement, then f of x is positive. Okay, not 0. No, not always positive. It might be negative also, but non-zero it is. Okay. So let's proceed. Now what we want to prove, we constructed this function. We want to prove that this function is continuous on A and not on A complement. So to see why it is continuous on A, so fx is 0 whenever x is in A, right? So for x in A, if it converges to xn is a sequence converging to x in A, then we want to prove that fxn converges to 0. So now if this xn are from A itself, then fxn is equal to 0. Okay, so we divide it like this. It can come from A. If it comes from A, then fx is equal to 0. So it is not a problem. Now, if it doesn't come from A, so if the sequence xn comes from A complement, then what is the case? We have, then xn is in this. Now, if xn is a sequence converging to A, which is in A, and xn is in A complement, then first thing we'll see is that xn can't be from a, like, xn is in infinitely many of these fn's. Okay, it can't be from a fixed fk. And why is that? That is because fk is closed. So if some sequence in fk converges to some point, then that point is also in fk, but A is in A, so A is not in fk because A is not in A complement. So if we have to get a sequence xn converging to a point in A from A complement, then xn takes, like, for that xn, like, there are many points in the sequence which are from arbitrarily like tail of the fn closed sets. So for that, yeah, so then this what we see is, so they are from different fk's, and for that the limit will be 0, right? So that is the case. And so we are just applying this here, that if a sequence is from A and A complement, like, we can divide the sequence into 2 parts and both of them converges, then anything union of them also like taking from both the sets also converges. So that is the basic idea here. This is a fundamental thing we did in real analysis. So what we see is that for any point in A, f is continuous at that point, right? Okay, so why is that? Again, just going to it, if the sequence xn converging to that point in A comes from A itself, then it is 0, so not a problem there. If it doesn't come from A, then it comes from different, like, many different fk's. It can't stop anywhere. So we need to go on, and so this thing will be 0, the summation part, the limit will be 0. And okay, so this is now we prove that the function is continuous at all the points of A. So we prove this part, that this is something we proved. Now we want to prove that for any point which is not in A, the function is discontinuous at that point. So let x be a point in A complement. Okay. So we take two cases. The case one is that x is in the interior of A complement. If this is the case, then what we do, we see that there will, so everything is non-zero here. Okay. So we will see that there is some sequence converging to it. We take the sequence from B. If that is the case, then they are always positive. Or just take the value of fx there. We can do that also. Take the value of fx. So if fx is positive, then you can take a sequence from, what was our definition here? Yeah, so gx minus half. So yeah, if it is positive, we can take a sequence from B complement, which is also in A complement. So that will go to something which is negative, because, or might not go to anything. But for any neighborhood around x, we'll get some negative number and positive number both, if we take the sequence from B, because B and B complement both are dense in x. Okay, using that, we'll get in any neighborhood around x, we'll get some strictly positive number and also some strictly negative number. So, and this will imply that it can't have any limit here, like it can't be continuous at x if x is in the interior of A complement. Now, if x is not in the interior of A complement but is in A complement, then what does that mean? That means that there is a sequence coming from A to x, right? And if that is the case, then f of xn for all this sequence is 0. So there is a sequence of 0 going to that f of x, and f of x is not 0. So of course, it is not continuous at any point which is in A complement but is not in the interior of A complement. So what we prove is that f is not continuous at any point in A complement. So we're able to prove that CF is a subset of A. So what we prove is exactly CF is equal to A. And A was any given G delta subset of X. We got a function which is continuous exactly on A from X to R. And X is a perfect metric space. Okay. Okay. So another thing we can notice here is this function is exactly, this function is 0 on A. Fx is 0 on A. Something we'll see later. Okay. So great. And now we have this, the most, you can see the most important theorem in the presentation.
Hello, I have
Yeah.
a question.
Yeah,
So
sure.
the theorem you proved, is that exclusively for perfect metric spaces? I mean, perfectness is required. I can see where it's required in the proof.
Yeah.
But
Like
is it exclusively.
yeah, we saw the counterexample, right? If we have some isolated points, we can take
Okay,
a
okay.
G delta subset which is not containing some isolated point, and for that we'll never get a function which is continuous exactly on that subset.
Okay, so that example that works if we have some isolated points, not all points are isolated or something like that, right?
Yeah. So so perfect metric space is a metric space which has no isolated points.
No isolated points.
Yeah, so suppose we have a metric space X with some isolated point, say A, then just take, and suppose X is, yeah, so if maybe for singletons it might work.
Okay.
Suppose
okay.
there is some other element in X which is B and not equal to A. So take B, this is the G delta subset of X, right? Which doesn't contain A. So you will never get a function from X to R which is continuous exactly on B, because it must be continuous on A too, right?
Okay.
So that's why we need the G delta subset which contain all the isolated points. Yeah. So so this is something we are able to prove, and this is quite a strong result. Maybe the proof is, of course, the proof is not very difficult, not difficult at all, but this can be used in many certain cases, but I won't go to the applications now because we have less time and we need to cover something else too. So this is something we proved. Now we go to a slightly different direction of study. And what we study is continuous and discontinuous extensions. So what is a continuous extension? Let X be a metric space. Let A be a subset of X. Then if we are given a function which is continuous from A to R, then we say that f is continuously extended to a function g from X to R if the restriction of the function g at A on A is f and it is continuous function. Like the set of points of continuity is the X. Okay. So I wrote this because we just learned this notation. It can be written as a continuous function. That is, we can extend it to a function which is continuous in the whole set and whose restriction on that subset A is the function we are given f. Okay. So in this case, we call the g to be a continuous extension of f and f to be a continuously extendable function. So similarly, we define something as a maximally discontinuous extension. So what is the idea here? What we do here is given a subset A from like in a X, so given a function like this, we want to extend it in such a way that in the other points too, it is continuous. And we want to do the exact opposite here. Given a continuous function from A to R, we want to extend it in such a way that it is kept continuous on A, but it is not continuous at anywhere except A. So that is what we need. So what is the definition? The definition is given a continuous function from A to R, we say that f is maximally discontinuously extended to a function g from X to R if the set of points of continuity of f is exactly A and it is an extension of f, like the restriction of g on A gives f. And okay, so again, the similar nomenclature, we can say that g is a maximally discontinuous extension of f and f is maximally discontinuously extendable if there is a function like this g. Okay. So now what is the thing we are relating to here, like what we want to do here? Okay, so before that, let's see a theorem on this continuous extensions, a very famous theorem, which says that given a metric space X, and let's see, it's a metric space version of it. It is a more general theorem on topological spaces, some with some normal and other restrictions. Anyway, so given a metric space X and a closed subset of X, C, and a function, a continuous function from C to R, there exists a continuous function from X to R whose restriction on C is f, small f. Okay, so that means that a continuous function from any closed subset of a metric space is continuously extendable on X, the bigger set, the bigger metric space. Okay, so just some fun exercise, not fun also maybe, but anyway, we just want to check if this is true for any G delta subset. Like the restriction of closedness is if it is replaced with G delta being G delta. So of course G delta is more general than a closedness. Any closed set is G delta, but not the other direction. So can we say that given any G delta set and a continuous function, any continuous function on the G delta set is continuously extendable? So can we say that? So you can think about it a bit, but the answer is no, we can't say that. Of course, the answer will be no, because otherwise the theorem would stated G delta, because it's quite a famous theorem. It shouldn't be so easily.
The theorem doesn't what if C is open, right?
Yeah, exactly. Yeah. So like not for all open, we can just take an example like this.
Yes.
Yeah. So this can't be, you can just easily check that this is not extendable continuously on R, because yeah, the thing is like this. So what is it? Yeah, something like this. Yeah. So this point you can't define it to any value which will give you the continuous on 0. Something on that line will work. Okay, so yeah, so what we want to do here is try to make some analogous theorem of this for maximally discontinuous extensions. This is a theorem for continuous extensions, right? So yeah. So what we'll do is this. What we try is this. Given a G delta subset of a metric space containing all the isolated points, a continuous function from A to R, can it be maximally discontinuous? Like, is it always maximally discontinuously extendable? Okay, so let's just take some time and understand what we are trying here. We're trying to get a function g from x to r such that the cg is equal to a, that is g is exactly continuous on the set A, and if g is restricted to g is restricted to a, it gives you f, small f, and small f is a continuous function on A. This is something which we have. Okay, so why G delta subset containing isolated points? Because in other case, it is of course not true. That we proved before. That suppose we are working with something which is not G delta or doesn't contain all the isolated points, then of course CG can't be A. We have categorized all the sets which can appear as set of points of continuity. So if A is like this, implies that A should be G delta and so on. Like A should be containing all the isolated points and such things. Okay. But again, this is something which is new. Like we haven't proved this before. So what have we proved? We proved this. Like this is kind of something stronger of the thing we proved. We proved that given a G delta subset containing all the isolated points, we can have a function from x to r which is continuous exactly on that A. But we constructed the function. So here we are letting the function to take any value on the set A. But there that was not the case. We are constructing the function in our way. And the function we constructed gave that fx equal to 0 for all x in x. So the notation is slightly changed and just all x in x. Sorry. This was okay. Sorry for that. So we already did it for all x in A, fx equal to 0. So if the function given is the 0 function on A to R, then this can be maximally discontinuously extendable on x. Like for this function 0 from A to R, we can get a function g from x to R such that the restriction of g to A is f, that is 0, g is 0 on A, and it is continuous exactly on A. This is from our construction. We can construct the function in the similar way we did to prove that given any G delta subset of containing isolated points, we can get a function which is continuous exactly on that subset. Okay, so this is something we did. So now, so this will imply what we proved before. If we can do this, then we can do that. So this is a little bit stronger statement of what we are trying. So this is the place where what we studied before and what we are studying now relates. Okay. So now we want to prove this, and this is true. Okay, this statement is true. And we want to prove this. So how to prove it? We'll prove it in 3 steps. Okay. So we'll prove this assuming that X is a perfect metric space. So in any case where we are doing like this, how we can extend this, take set X metric space, we can write it as X dash union H, where H is isolated points of X. And then X dash is a perfect metric space. So then you can see that all the theorems will be extended like this only. Okay. So this is just a matter of trying. Anyway, so assuming that X is a perfect metric space, we want to prove that firstly, we want to prove this. Given any closed subset A of a metric space and a continuous function from A to R, we will get a function g from X to R, which is continuous exactly on A and whose restriction to A is F. Okay. So this is a weaker thing. Like first we prove something which is weaker. Finally, we want to prove it for any given G delta subset. So for that, we are building our steps, and first we will prove it for any closed subset. So where we have seen closed before in the Tietze extension theorem, there we have seen the closed thing before, that for any closed set, the function on that is any continuous function from if A to R is continuously extendable. And we want to prove that it is also discontinuously extendable if the metric space is perfect. And then we do it for dense G delta subsets, which is also a bit more restricted than a general G delta subset. And using this too, we'll finally prove that it is true for any given G delta subset of A. Again, what we want to prove finally is, given any G delta subset of X and a continuous function on that G delta subset, we'll get a continuous function, we'll get a maximally discontinuous extension of it. That is, we'll get a function X from G from X to R, such that C of G is equal to A and its restriction to A is F. Okay. So this is basically the last thing we're going to prove here. So, and the proof is a little bit long. Let's see how we can manage this. So yeah, to begin with, step one, what we have is a closed subset. So we are applying the theorem we learned, and we are also given, we have a closed subset and we're given function A to R, which is continuous. Now we can extend it to, sorry. Yeah, we can extend it to a G1, which is continuous function on X and whose restriction is F. Okay, this is by the Tietze extension theorem. And again, we can have a function G2 such that G2x is equal to 0 for all X, and G2 is continuous exactly on A. This is how, this is from the way we constructed in while proving this. In a similar fashion, we can construct a function which is 0 exactly on A, 0 on A, and which is continuous exactly on A for any closed set. A closed set is a G delta set, so we can do that, right? So okay, so if we do that, then we take the function G to be G1 plus G2. So now G2 is 0 at A, so we can say that Gx is equal to Fx, like G1x equal to Fx for all X in A. Okay, because G1x is equal to Fx because it is extension of F. Okay, so the function G is also an extension of F, and also it is continuous exactly on A. Why? Because G1 is continuous function, like continuous on X, and G2 is continuous exactly on A. So okay, you can check it, like it is, yeah, very easy to check that it is continuous exactly on A. Anyway, so okay, I think we have to go a little fast. Then we are going to step 2. So we proved this. What we proved is this. Step 1 is done. So to prove that if we are given a dense G delta subset of A, then also we can get a maximally discontinuous extension of F, a continuous function on that dense G delta subset of A. Okay. So how to prove that? So given a G delta subset A of X, again A complement is F sigma. Then if A complement can be written as disjoint union of closed sets, we can take some union of closed sets and then make it disjoint. Okay, so a similar trick as before, we are just making them disjoint and then writing A complement as disjoint union of closed sets C1, C2, and so on. Okay, we are also given a function F. So what we are given a function, a continuous function of A to R, and A is a dense G delta. So now we define a function kx, which is equal to n if x is in Ci. Okay, so this is a unique n, of course, because the Ci is a disjoint. So if x and okay, so this is for x in, yeah, okay, so x in Cn means what? X should be in A complement, right? So kx is defined for all x in A complement. For x in A complement, kx is defined. So now what we want to see is just something we'll need after this, that if xn is a sequence in A complement, okay, like xn is in A complement, and xn converges to some A in A, then kxn tends to infinity. Again, similar to what we did before. So all the ideas are very similar here till now. Okay, and why is that true? Because if I is Ci is a closed. So it can't be repeatedly taking xi's from a single set, because then the limit point of it will also be in ci, and then it can't be in A because ci is a subset of A complement. Or no, yeah, like, yeah. So yeah, so we prove this here, and then we go to this. So now as A is dense in X, A is dense in X because we started with taking a dense G delta subset of X. We can talk about taking limit of any other point in B in A complement or B in general X. We can take a limit converging to B when the xn is coming from A. Right? We can take that. Now, so this limit makes sense. And this may or may not exist, of course. So let's say B1 for all the B in A complement for which it exists, and B2 if it doesn't exist, all the B in A complement. So A complement is actually B1 union B2, right? Okay. Now see that if we can define FB for B in B1 in this fashion, because the limit exists. And this is a continuous extension. You can check it. If the limit exists, you can just define. So f was a function from A to R. So f is not defined on anything which is not in A. So now we are defining f outside A in like FB as the limit of fx when x is in A and converging to a point B. If the limit exists, then this FB can be defined in such a way that it is continuously extended. Okay, but remember we need a discontinuous extension, not a continuous one. Anyway, so okay. Now as A is dense in X, for each X in A complement, we can choose AX in A such that this happens. Now we want to do something for this B2 set. Okay, we did something for the B1. Now we want to do something for the B2 set. We need to define a function on the B2 in some way, right? So what we are doing is for any X in A complement, we choose a AX in A such that distance of AX and X is less than 1 by KX. Remember what is KX? KX is the coordinate of the CI where X is, and which will tend to infinity, like which will be arbitrarily large if there is a sequence converging to something in A. Okay, so now we define a function h from A complement to R as hx equal to ax. We take some ax. There can be many ax of this form, and there is, we take some ax, fix some ax. And we construct, now we want to construct a function g from x to R, which has all the properties we need. That is, which is an extension of f. First of all, for this we have defined it in this way. And then we need that is which is continuous exactly on A and not outside A. So for that we define it in some way and then prove that it is actually the case. So how we define for x in B1, what we do is we know what is fx. We define it in this way. The limit of fx when x is converging to B from A. Then we take plus 1 by kx. Okay. And for B2, what we do? For B2, we take f of hx. What is hx? Hx is the ax, a element of A, which is very close to x. And f is defined on any element of A. So f is defined on hx, of course. Okay. So that is something we do. And then we go to how we prove that Cg is equal to A. G is extension of f, that is clear. Now we want to prove that Cg is equal to A. So for A, we want to prove that it's continuous at A, right? If xn is a sequence converging to A. Now, if xn is in A, like a sequence from A converging to a point A, xn, okay, then of course, all the values are matching. G of xn equal to f of xn, g of A equal to f of A, and it converges properly. If not, if xn is coming from B1, then what happens? Then for all n in n, kxn goes to infinity, right? As n goes to infinity. So limit of g of xn can be written as limit n tends to infinity f of xn plus limit this exists, so 1 by k of xn, which is 0. So this remains to be the thing, and here xn, of course, we can define it this way. So this is equal to f of a, right? Okay, and hence g of xn converges to g of a, and this is the case when xn is coming from b1. Now suppose xn is coming from b2. Okay, so if xn is coming from b2 for all n, then hxn is going to a as n xn goes to a. And why is that? As we defined hxn is a point in a which is very close to x, and for here it is a. So as xn goes to a, hxn goes to a, and thus f of hxn, and hxn is always a point in a, right? Yeah. So h of xn is always a point in a. So we get a sequence hxn going to a in a. So again, from this part, we know that the f of h of xn also goes to f of a as n goes to b. So this is also true if xn is coming from b2, and a union b1 union b2 is the x. So again, that thing we used before, that if it comes for all the different sequences converges, and a sequence is taking elements from all these disjoint union things will also converge, like continuity will be maintained. Okay, so what we prove is that CG, yeah, CG, now what we prove is that A is a subset of CG, that at all the points in A, the function is continuous. Now we also have to prove something else, which is that G is discontinuous on A complement. And that is not very hard to check, because if B is in B1, then take a sequence xn in A, we can take that, right? Because A is dense. Then gxn converges to f of B, but how is the definition? The definition is f of B plus 1 by k of B. So this is something finite if B is in A complement, right? So this is not equal to f of B, so the limit doesn't match, and thus it doesn't converge to g of B. This is g of B, right? Okay. So G is discontinuous on B1. Now why it is discontinuous on B2? Because for any B in B2, the limit of y goes to B when y is in A doesn't exist. So it is trivially discontinuous on B2. Okay. So what we proved is that CG is exactly equal to A. Okay. So we are able to prove this. Step 1 we proved, step 2 we proved. So we have that for any dense G delta subset of A, and given a continuous function a to r, there exists a function which is extension of f, and which is continuous exactly on that dense G delta subset A. Okay. So now we want to prove it for the general G delta subset. Okay. So how to prove it? It is not much of a work to prove that. Okay. So what we prove is for any A, now A is a general G delta subset, right? And f is a function which is continuous from A to R. Now what we do? What we do is take B to be the limit points, set of limit points of A not in A. That is A closure minus A. Okay. And so just see that when you take x minus b, what is that? We are just subtracting all the limit points of A which are not in A. So this will make that A is a closed subset of this, right? Because all the limit points of A is in A itself, because if it was outside A, it is already in B, so it is not anymore in x minus b. Great. So it is a closed subset of x minus b. Now, in case 1, what we saw, we saw that now, so given a function f from A to R continuous, we can extend it to a set. Now, what we do is extend it to a something like this. Take this G. So why can we do it? Why can we extend it discontinuously? Because this is closed in this, and by case 1, if A is a closed subset, we can do that. Okay, so we did that, and now we get a function g from x minus b to r such that cg is exactly equal to A. Now again, okay, so what points are left? We need to find the value, the the values of the function at the limit points of A which are not in A. Except that we know a function which is discontinuously extending the function f. Okay, so for that we take A closure. So A closure we take, and A is a dense delta subset of A closure, right? Of course, you can just take in subset topology, the complement. Yeah. So A is a dense delta subset of A closure in the subset topology. And hence, by case 3, in the case 3, what we did, if there is a dense delta subset, then it can be, and a function continuous on it, it can be discontinuously extendable over the bigger set. So we again extend it discontinuously from A closure to R such that it is continuous exactly on A. Okay, and observe both this H and G both are extensions. So G in A is also F and H in A is also F. So they don't contradict themselves on A. So now we define a function capital Fx to be hx when x is in A closure and gx when x is not in A closure. And we claim that this is a maximally discontinuous extension of F. Not very hard to see. Why? Because okay, so what we want to prove is that this is continuous exactly on A. So this is continuous on A because any sequence converging to a point in A, the function values also converge because they are either from this or from this, and both are continuous exactly on A. And why it is discontinuous? Similar way, right? So what we do is like the main idea behind it is like this, that we divide the whole set into a set A and then the outside limit points of A and then the other whole part. Okay, the other whole part. So this is closed in this whole thing, and this is again like in minus this thing of that thing. This is closed in this whole part, and this g delta and dense in this whole part. And we give some value to this and give some value to the other part and take the whole thing, and that will give us the bigger function which we are defining over the whole capital X with our desired property. Okay, so what we are able to prove is that given any general G delta subset of a metric space X, which is a perfect metric space, and if we give a continuous function from A to R, there is a function G from X to R such that it is extension of F, and it is continuous exactly on A. Like we're extending it without making it continuous on any other point. Okay. And again, if we remove this perfect metric space, we can add it a G delta subset A containing all isolated points. Okay. And yeah, so that is what we are doing, and that is what we wanted to prove. So we are done almost. So let us just sum up what we did in technical terminology. A topological space is called a DEP space, which is from discontinuous extension property. If each function f, for each function f in A to R on a G delta subset has a maximally discontinuous extension. This is a maximally discontinuous extension. Okay. So there are a few other ways to define a discontinuous extension, but okay. So what we proved is any perfect metric space. Okay, so this is something type of are DP spaces. Any perfect metric space is a DP space. And also one more thing, this is not true for a general topological space. Not all perfect topological spaces are DP spaces. Okay, we have counterexamples in with many restrictions too. In perfect separable Hausdorff, we have counterexample. Of course, if the topological spaces are metrizable, then it is true, because again we can work on the metric. The counterexample is not very easy to construct, but it's not very difficult to. Anyway, so that was it. Let's sum up what this is this is a stronger result than what we proved before for the other direction of it. The first direction is totally unique, that any set of points of continuity must be a G delta subset. Then again, what we tried is, for any G delta subset, can we give a function which is continuous exactly on that? But now we have given any continuous function on G delta subset. Not only there exists a function. For any given continuous function, we can extend it to a function which is exactly continuous over that G delta set. So this is again quite a strong result, and quite a good result to say. Okay, so I think we can end our discussion here. What is the time? Yeah, the time is also fine, I guess. Yeah, this work was very much motivated by my professors Jaydev Sarkar and Shomushan Naik. So I would like to acknowledge their help and suggestions, and also thanks to the organizers for organizing and inviting me here. Yeah, I think we can stop now if there are any questions. Okay, so if there are any, yeah.
So the first theorem that we proved, the earlier one, that was true for general topological spaces, right? The last one was probably not true.
Which one was true for general topological spaces? This one.
Yes, yes.
This extension theorem, Tietze extension theorem.
Yes.
Yeah. This is with some restrictions. I guess we need normal and separability.
Okay.
Yeah.
But the latter theorem, that was.
Yeah. The next theorem we need the metric space thing. Otherwise, yeah, from the beginning part we are using that diameter thing, the distance property of it. So it is not true for general topological spaces. Yeah.
In middle, you were trying to tell some applications about of these things. So can you indicate something?
Yeah. Applications of the first part. Like this part also must have many other applications, but yeah, the first part, like the irrationals, rationals thing, we can think over like other subsets, close 0, 1. So we can think to have a function which is continuous exactly over here, or something like a more difficult set. And for all that, the construction we did is giving a function which is exactly 0 over that set and exactly continuous over that set. So such functions can help to merge to function and give some good results on it, because they're continuous over the space. And like for any given set, we can make a function which is continuous over there and discontinuous outside. And then if we sum it with some function over some closed set, and like that, the 0 part is in many cases helpful. That is a kind of use of that construction. Like we use that here also, right? Like this is a very wonderful case where we are using all the things we are doing in the next thing we are trying to prove. So that's why, like in any such extension or anything like that, which speaks about continuity of points and the set over which is continuous, it's helpful to have a function which is 0 there and like that, continuous outside it, continuous on exactly on it. So if there are any other, I can't see the chat. So yeah. Thanks all to bear with me in the presentation, and sorry for this cracking voice. This season change is really very. Anyway, I think if there are no other questions, then the organizers can end the meeting.
Yeah, Soham, thank you for the talk. It was a great one. And, so we end the session now, and join us on 27th for a talk by Tarushi on the proof of the prime number theorem using elementary techniques. Thank you. Thank you very much.